And I'll keep an eye on the chat for votes as we go here. So there's a couple things that we have to do. The first is we can do a couple different variations. I'm going to start with a rectangle just for the sake of simplicity. So we're just going to throw a rectangle up there and change it with the smart dimensions. This is going to be 70 divided by 2 because it's half of the exterior. And that height we want to approximate. So this is a straight section, but it has a chamfer. So it's a little bit difficult to measure. So what we have to do is we have to line up one edge with the top and then approximate where that bottom edge lands. You can try and do it with the ID side of the calipers, and that'll get you pretty close. So this is right about 21 millimeters total height. So this side is 21 millimeters total height. And there is a fillet on this side. So in the sketch, there is a sketch fillet. This is something we haven't used yet. I'm going to go ahead and add it here just because of simplicity. The trick is we need to figure out just about how much that fillet actually is. I'm not going to recreate the curvature at the base. I'm just going to assume this is flat. So this is a simplifying assumption. This height, as it starts to curve, is a radius of, trying to get it proportional. So radius right at, yeah, it looks like about 5 millimeters. So that's what it measures. You'll get kind of a sense of what number to expect out of this the more and more and more that you do it. So we're now going to recreate the rest of the cup as a physical object. So the base is, the taper starts at the same diameter and then goes all the way out to a wide spot at the top that's probably going to be 80 millimeters if I were to guess. No, it's a little more of a taper than that. So it's probably about 90 millimeters. Yeah, so this is right at about 90 millimeters. There we go. So total 90 millimeters. It also has a height, especially if you have a limiting factor like a set of calipers that's short and only allows you to measure. In this case, this has a maximum of about 5 inches. So it's not useful for large objects, but you can measure 5 inches. So this is 5 inches to the top of the N on the logo. Or actually, this is 90 millimeters to the top of the logo, and another from the top of the N or some other designating mark that you can use as a reference point, something that's fixed. Another 65 millimeters. So 90 plus 65 is what our total height will be. So what I'm going to do is create another rectangle for the sake of simplicity. And what this will do is we need to have a total width of 90 divided by 2 is our top point, and our height is going to be that same set of values. So it was 90 plus 65 millimeters is 155 millimeters in total. Now the difference is we need this to match up to the top up here. It actually happens, there's a little bit of a flat spot on the top that is, again, it's going to be, a lot of times you're going to find some symmetry in design. So it's going to be that same about 5 millimeters before the curvature starts, just because reasons. So you're going to add a little line segment, and you're going to make that 5 millimeters. And then you're going to bring this in from the end of that 5 millimeters to the base here. And you're going to trim this and this. So now we have our starting point. I'm also going to trim out this ridge because we don't need it. I'm going to trim that center line. I'm going to trim that center line as well. And what we're going to do here is we're going to add a center line down the middle for use later, before I eliminate this line using the trim entities. And what we're going to do instead is we're going to bring this in. The actual thickness is, again, where you'll find that conservation and design. It's the same 5 millimeter thickness, because 5 millimeters is about what it ought to be. And then we're going to use a clever, a clever tool here. So I'm going to set the width of that to be about 5 millimeters. Okay, so now we have some of our exterior shape. And what we're going to include is we're going to make use of this offset entities. And we're going to select these segments here. We are selecting a chain, and we're going to use a 5 millimeter thickness. We're going to reverse the direction. I'm going to do this in a couple segments. And yeah, I'm going to do this in a couple segments. So first, this lower piece, just because this is a thing that's going to give us some, there we go. If I reselect it as a contiguous chain, I can now reverse it to get the spacing internal, and I will have a thickness, a wall thickness of 5 millimeters. And I will have the base geometry. So if I hit OK, what I can then do is I can then do another sketch fillet, because they're almost never exactly rounded here. But it's not going to be 5 millimeters. It's actually going to be usually much less. It's going to be about 1 millimeter. So it's going to be very small, but it's going to be rounded ever so slightly there. So we have our sharp base here. I'm going to eliminate this top line and the dividing line here. I will, however, need to make sure that we have a line connecting the base. And as long as these guys also often will be filleted by 1 millimeter. And thing with these two, about 1 millimeter fillet, might be a 0.5 millimeter, sort of depends. All right. So what we've got is now all the key pieces to be able to revolve a volume. Um, we just want to make sure that we've got enough because there may be a couple lines here that have been there may be a couple lines that have been altered in their function. So I'm going to see if I've got enough information left. Okay, so the sketch is currently open. Um, so what I'm going to do is I'm going to close out this geometry. That's what I was checking. Sometimes when you go in and eliminate something that has a relation like that, you'll have to fill it back in. So you'll recreate a, you can kind of do a conversion to an arc using some minor mouse wizardry. Um, that's a thing that you have to swirl it around the correct number of times. I don't remember exactly off the top of my head what that number is. So now we have our closed geometry and we know what to expect in terms of how this geometry behaves. So we're going to do a revolve of this shape. So we're done using lines. I'm not going to focus too much on, again, the dimensioning and making sure this is a fully defined sketch because reasons. For this specific example, it doesn't matter. But what I'm going to do is revolve it around this line. And all of a sudden, with a few minutes of effort, I have now made a faithful recreation, hollow interior and all, of the travel mug that I'm using. And that probably took far less time than you guys expected, right? Plus one in chat if you think that's a little bit more efficient than trying to do an extrude base boss from a circle. It's a lot better, right? So see, instead of just taking up class time to teach you guys how smart I am, I would much rather actually use and recreate and work on real parts. And that only took a handful of minutes. So we will get to the point where you guys should have enough practice that you will go to do part recreation from a 2D drawing, and it will only take you a few minutes. Because of that, or in order to get there, in order to make that work correctly, in order to make that cooperate and do the things that are needed, we've got to get practice, recreating absolutely everything we can in SolidWorks. So the more you can live, eat, and breathe SolidWorks drawings, you're going to be much, much better off. So, all right. Any questions on that process or something that you want me to wait, go back and do that again? Most of you should, based on what I've seen from the work that's turned in, be able to follow that pretty easily. So we've got another part to recreate if there's no major questions on this. Um, yes, the first object, let me double check that this is what I think it is. creating 3D models from physical objects. So that's what I want you guys to recreate, is show some dimensions that you took off of a real uh, a real cup, a real water bottle, a real something. And even if you do use extrudes because you're more comfortable with those rather than a revolve, that's okay. I just want you to recreate as much of the detail in that real object as possible. So very often Dr. K will bring in a plunger to class. I have a plunger, but as I'm not certain how often it's been used, I'm going to decline the opportunity to take measurements with it and recreate it. Just reasons. So yes, that's what I want you guys to do. That's a way that you can very realistically make some of these kinds of parts from real objects. You will get to be faster and faster and faster at this with more practice, but that's what you want to work. That's what you want to work on. All right. Yeah, the other parts tutorials are showing you how to use a couple things, some revolves and sweeps and fillets, pattern features, design tables and equations. You can get to the same kind of object. I guess it probably makes sense for me to recreate another version of this before we go do this next part type. So I'm going to recreate this using the same concept. The problem is, in order to just start with a circle base, as a lot of you suggested, the base for this was 70 millimeters. In order to make this work and do the same kinds of features, there's a few more steps. So I'll go ahead and show those to you. So we start by extruding upward 21 millimeters, and that's our first base. Now, from here, we're going to do another extrude, and we can actually make use of the first sketch that we did. We do that by selecting our part tree, selecting the base sketch, and saying, now, instead of a blind extrusion from the sketch plane, I want to extrude from a surface, face, or plane. I want to start up here at the top of my object. I want to start at that top plane, and I want to do a blind extrusion, and I want to do the total height needs to be, that was 65 millimeters plus 90. So 155. The problem is I need it to actually be an outward draft, and I need to figure out approximately how much that tapers out. So how I do that is by working through the trig relation. And I can see just by looking at it that we are not quite there exactly. So this probably needs to be, as a minimum, about a 2-degree draft. That looks closer, but I think it's going to need to be, it may actually need to be about a 3-degree draft. That seems closer. So how we can then check that is we say, all right, that looks probably pretty close. How we can check it is using evaluate. We haven't done this a lot, but we're going to use the measure tool. And we want to measure what the outer diameter of this is. So the outer diameter, remember, needed to be about 90 millimeters. So 86, pretty close. It looks like the correct aspect ratio. Probably a few of you are like, what in the Sam Hill is an aspect ratio? It is a ratio of one dimension relative to another. So the angle and ratio of the two diameters is close enough that I can tell this is within a reasonable approximation of what the actual object is. So the aspect ratio is close enough that I would count this. So actually, what we need to do is alter that boss extrude by editing. So you do a right click and you edit that boss extrude, and it actually needs to be about 3.5 degrees. I think is going to be a little closer. Then we measure again, and that is now 88.96 millimeters. So 3.5 degrees is about right. That's probably within the tolerance of my actual measurement techniques. I'm going to take it one individual step further just because. So I'm going to bring this to about 3.75 degrees, and that should get us almost right at 90. Yeah, so 90.32. Okay. So we're right in that ballpark of where we want to be. We can fine tune that and go back and forth, but this is a much more manual method of correcting the entry. So 3.7 degrees is, we're going to call that spot on 90.05. So now we've got the base. One of the techniques you guys are going to learn is the feature operation here. You're going to have to do an extrude cut because this is a solid object, but you're also going to have to do some filleting. So you're going to learn how to use the fillet tool. In this case, that's quite a bit too far. We decided that measurement was about 5 millimeters. So the fillet on the 3D object mechanically gives you the same feature compared to, let's see if you're even seeing, yeah, you're still seeing it, okay. So the active SolidWorks window is what should be there. So compared to this object, we have the same feature as this object that's solid, right? So we've done the same operation just by a different means. So this part is going to be identical after all said and done. The top part of the object is what we need to work on next, because the base is done. The outside is just about done, kind of, sort of. And I'm actually going to have to do a little bit of additional work there, and then do a cut in order to recreate this part of the geometry. So I'm going to go back in and make adjustments yet again to this extrude, and it's actually going to be about 3.8 degrees. I'm going to verify that that is in fact beyond our 90 millimeter. Yeah, so we lose an extra millimeter here to get the geometry that we're looking for. We now need another sketch. So we're going to have to do, we're going to click up here and we're going to add a sketch, which is a cheater way to do it, but that's okay. When we select a plane and we add a sketch on that plane, we get an example of how to make this work a little bit better. We're going to do our 90 millimeter diameter. So 90 divided by 2. We're going to do our 90 millimeter cut. I'm going to make another circle that is wider than one. Yes, we will go over how to make threads. I'll show you a modification. That'll be a little bit easier. There is a tool like in Fusion. We're not going to get to that yet. It's something called a loft, where you can change diameters, but a loft is only going to create a solid object if you don't also do a loft cut. So that's another aspect of what we have to keep in mind. So this right at 90 millimeter, we're going to have to make a couple more kind of fine tuning adjustments here. Because we've got a very small region of overlap here. We're going to need to make that, let's see, we're going to need to make that, yep, that taper has to be 4 degrees because reasons. So yeah, I'll get to some of the cool stuff. Yeah, the internet is problematic. All right. We're going to leave that circle. I'm going to make one more edit so I'm going to step out of that sketch. I'm going to make one more edit. And this needs to be 4 degrees. 4 degrees, that's going to be a whole lot closer. Okay, 4 degrees might even need to be almost, yeah, 4 is pretty close. All right, so then what we're going to do is we're going to do an extrude cut. So again, I'm trying to constrain myself to using only the existing features here. So the extrude cut, I'm actually doing a cut almost as if it were with a circular hole saw. And what that does is cleaves the top of my object, so I can now go back in and make some fine-tuning adjustments to this angle. So actually maybe it only needs to be 3.85 degrees. Check. All right. So that gives us more or less, you guys are starting to see why the actual math and trig would be a lot faster. The difference between these two, center distance is about 6.4, so it's still a little bit less than this. 6.4. So we're going to make one more edit to that. So our original, so our 3.75 actually might have been correct. That looked correct. So let's take a measurement between these two circles. Center to center, no, that's not what we're looking for. Measurement. Center distance 2.7 or 2.43. Yeah, not particularly helpful. So it is a steeper taper than that. So we're going to go with 3.8 right in the middle. So we've danced around that 3.8 a little bit. That's going to get us pretty close. 4.4, that's going to be close enough for this particular application because we're trying to faithfully recreate the same detail as what we did here. But here it took us just a couple of minutes to do this. Now we need to do yet another operation. So we've got our flattened edge and our angle. And what we need to do now is our extrude cut. So we need to add another thing to this top sketch. Nope, not that one. Top sketch, sketch 2. And we know the exterior diameter is 90. We know that the wall thickness is 5. So we know what we need internal to this to do our cut. And it needs to be a circle. So this needs to have a radius of 40 to give us the 5 millimeter wall thickness on either side. that 10 millimeter overall diameter difference. We need to account for half of that. So we really have to pay attention to the geometry here. So we're going to step out of that sketch, exit the sketch and rebuild anyway. We now need to redefine the cut extrude because the selected region needs to be this region only, not the whole region. So we now get our redefinition and we get our rebuild error Y. Clear selections. So this region is what we need to do our cut extrude. Well, it no longer intersects the model now. Okay. So this, we may have to delete that cut extrude and redo it, make sure that our angle is still about 3.8. So it's really about 3.82 degrees. Okay. Sketch 2. Now we're going to do an operation to sketch 2. We're going to do an extrude cut. We want to select specifically this region. Does not intersect the model. Why? That is very, very strange. So something changed. I need to set the smart dimensions here. 80, yes. 90, yes. And I'm going to do 100 for that one. So there is an intersection with the model, and I don't know why it's giving me smack talk, probably just because SolidWorks wants to demonstrate that it in fact is the master of all its surveys. And just because you think you're Mr. Smarty Fancy Pants going to do some operation on a sketch does not in fact mean that you are going to be able to do any such thing. Doesn't intersect the model. Yes, it does. That's very strange. So I don't know why we're getting that error. We're going to lose that particular feature based on what I'm seeing here because reasons. So I'm going to try another extrude cut and see if it's just this sketch that's the issue. If we do just a straight extrude cut, you see, that's not going to work. So we have to do a taper, and it has to be the same angle, 3.82 degrees. Okay, and it's going to go all the way to 155 plus 21 minus 5. So 155 plus 21 minus the wall thickness of 5 is 171 millimeters. Okay, so we've done a cut. We now need to do a fillet down here of 1 millimeter to recreate that detail. And we need a fillet for 1 millimeter on the interior lip there. Okay. Then we need a, here we can do a chamfer actually, since the extrude cut is not behaving. But we're going to set the dimensions of both along this. And so edge 1, we need to start with 1 millimeter chamfer on this edge. Now I need asymmetric and I need to control the parameters. So we actually need 5 millimeters on one edge and 1 millimeter on the other edge. And you need to kind of figure out which is which. So 5 millimeters on the one edge and 1 millimeter, it's actually going to come down to less than 1 millimeter, and it's going to be 0.05 millimeters, I think, or something like that. And what this is going to do is give us our very small cut. Let's do 0.01. This is going to, or 0.1 rather, not 0.01, 0.1. This is going to get us close to our vertical cut using the chamfer tool when the extrude cut doesn't work because it's a Monday in engineering. Sometimes those happen. I'm going to try 0.2 and see. Okay, so that looks closer to being vertical. I'm going to go ahead and apply that. That's maybe not totally vertical, but pretty close. Then we can come in and do our 1 millimeter fillet on the edge at the end. So we've managed to now force our way to recreate. There's really a slight angle there, but we can continue to make some more adjustments there. Make it 0.3 millimeters. Okay, that looks vertical. That looks vertical, or very close to. So this allows us to then reach the same level of detail as the other example using the fillet, the chamfer, the extrude cut, and making use of tapers and the measurement tool to verify that we in fact have our correct dimensions. So I'm going to go ahead and measure this outer diameter, 90.09. Yeah, so my last adjustment there to the fillet was exact, put it exactly where I need it to. So two different techniques, exact same dimensions. That's how it's done. Not that I'm a professional or anything like that. Okay, so votes. Which one was easier? The one with the part tree where we use boss extrudes all over the place, or the one where we do a single sketch and we do a revolve? Let's see those votes. Yeah, single sketch. Much faster, right? Took closer to almost 30 minutes to do extrudes and boss extrudes. Took like 15 minutes, less than half the time. And I probably could have done that in maybe 10 total to recreate the cup, including measurement time. That's the same thing that you guys will start to see before long. All right, so now we'll start recreating our next part. That'll at least give us a pretty good starting point. So let's do that. We're going to recreate yet another different part. Okay, so the part that we're going to recreate now is essentially an injection molded buckle. Okay, this has a specific design to it. It has a It has a couple design features that we're going to recreate. They'll be a little bit hard for you to see, but we're going to recreate the basis for this as faithfully as we can. And because I'm going to be 3D printing the part instead of injection molding it, there are a couple dimensions where I'll do some additional reinforcement in order to make it significantly stronger, because I can without losing any features for this exact part. So we're going to take a couple measurements and then start jumping into SolidWorks here. So I'll bring this back up. So what we're going to be doing is we're going to be recreating this. The base is a rectangle. So it is about 30 millimeters plus flashing. So 30 millimeters wide. So we're going to start, in this case, we're going to start a top plane. So we're looking at like a top-down view. So this is 30 millimeters. Most of this we're going to recreate from the top plane. Some of the features we're actually going to recreate using a mid-plane extrusion, so something you guys haven't seen yet. So I think that'll be helpful. So we're going to start with a base rectangle, and this is 30 millimeters. So I'm going to recreate the part first, 30 millimeters wide. Then I'm going to do the modifications to the part for purposes of additive manufacturing, to do some reinforcements, since I don't get like fiber-filled nylon as an option for this. I need to make it in a weaker material and therefore make it thicker and stronger, but still to do the same things. So 40 millimeters long. 40 millimeters long. All right. So this is the base for our geometry. There is a taper. It's really an uneven arc in terms of dimensions. The particulars there are not super extreme, but the arc starts at about 23, about 22 millimeters up from the base. So I'm going to add a couple lines of length 22. So I'm going to set their dimension 22. I'm going to set another line on this side so that I have a similar reference point for a 3-point arc. And there's another line that I'm going to need relative to, I'm going to use a center line for a couple different things in this geometry. Yeah. All right. So center line, and off that center line on either side, we're going to have the original base comes out to be about, let's see, 16 millimeters wide. So you can do what's called a midpoint line. This is one of the instances where you might actually use that. And it's going to be not the whole base, but the distance between these two needs to be 16. So now I have the reference point for the 3-point arc. And it looks something like this with the radius or the center line at the other edge, give or take. Let's see if I can get it to be exact. So somewhere right about there. The edge or the radius is actually going to be the radius is going to be just about right on that edge. For this point, it's not super important. What I'm going to do is set this distance that's currently 0.16 to be 0, and then this arc is fully defined. What I'm going to do is mirror that element. So I'm going to mirror this line, this arc, and I'm going to mirror it about the center line because we need center lines to do stuff and things. Okay, then we're going to cut away the excess geometry here just because we don't strictly need it. So yes, I understand. I'm eliminating things that parts of the sketch were dependent on. There's also going to be a rectangle. In this case, I'm going to do center point rectangles for both of them. So center point rectangles that are going to be, and you'll use the inner dimension, which is the backside of calipers. You'll use the inner dimension tool to make it a snug fit and flashing thickness. One side has a lot more casting imperfection from the mold than the other. So I'm going to use that, and it's exactly 5 millimeters. There's that 5 millimeters again. 5 millimeters is going to be a theme that recurs fairly often. So we're going to recreate these two slots, and we're going to see how these are related. So thickness wise, 5 millimeters, because these have to account for a 5 millimeter band between them. And the inner dimension, so these are technically cut out as slots. I'm going to do them as rectangles to keep them a little bit more simplified. So we're right at 22 millimeters wide. So there's that design conservation again, 22 millimeter. There's something aesthetically that happens when there's some symmetry. The rectangle ratio is such and so, etc. The wall thickness on this is 3 millimeters. Generally speaking, in 3D printing, a wall thickness of 3 millimeters is, if you want a strong part, the absolute dead minimum. The thickness of this feature is 4 millimeters. So the spacing between these two is 4 millimeters. And we've got another, we've got a hole that we're going to recreate that is from the base. The actual hole in the part is not necessary for the geometry, but it's nice to know that it's there. So it's 27 millimeters from the base. Yeah, 27 millimeters from the base. So we've got another rectangle that is 27 millimeters from the base. Using the ID again to get the spacing. That is 5 millimeters wide. There's that 5 millimeters again. And the width of this latch part is 9 millimeters. So that's really the only unusual version of anything I've seen so far. So that's interesting. Normally that would be about 10 millimeters. I don't know why they didn't do it that way, but it's 9 millimeters. That's the width that goes into the opening in the band, and we'll see kind of why that is in total. So our overall length between, yeah, there we go, here and here, 40 millimeters. Yeah, that's still correct. Okay, so 40 millimeters. So this is our base plate for the buckle. Like I said, we're gonna recreate the part as it is first. Then we're gonna look at it from a standpoint of additive manufacturing and look at where the weak points in the geometry are. So there is a base thickness here that we extrude the entire thing. We have a base thickness of, again, 3 millimeters, because that's the very, very minimum for something like an injection molded part. It's really, frankly, too thin to be a strong part for additive manufacturing. We'll get into why that is. Because this, if this were made like out of aluminum or something like that, and we were trying to 3D print a part for a casting, that would be okay. This would be an okay thickness in something like aluminum. It's pretty flimsy for something like a 3D printed part. We're going to add our hook. They have another sort of raised geometry that we're going to include here. So we're going to add a sketch to this top plane. So I'm going to go back to center the view over the top. So we're going to add a sketch, and we're going to add it to this top plane. And what it's going to be is it's going to be a bunch of corner rectangles. So this part here and this part here and this part here. We're going to do our smart dimensioning. So 4 millimeters, 4 millimeters, total height, 22 and a half is about right. 22.5. 22.5. We've got a wall thickness here of 3 millimeters. All right, so this part is then extruded in order to reinforce for the injection molded part. This region is then extruded by another from 3 millimeters to 4 millimeters. So it's a 1 millimeter extrusion. So again, we're recreating the part as it is first. 1 millimeter extrusion. Okay, so we have a little quote reinforcement to increase the thickness there, and to make sure that there isn't just a concentrated stress point right at this corner. You'll learn more about that in materials classes later. We have one more feature that we need to recreate, and we're going to do, I said, a mid-plane reference. So I'm going to insert a plane, and I'm going to use this as a reference point, and I'm going to use this as a reference point, and I'm going to use this midline down here as a reference point. I'm going to eliminate edge 1 and replace it with that point at the midplane. So once you select a series of points, you can make this work pretty easily. So this is a mid-plane. What we're doing is we're going to add another sketch. We're going to reorient our view. So we're going to add another sketch to this. We're going to right-click, say New Sketch on this, and we're going to reference part of this. We're going to reference part of this. It'll be a little hard to visualize, so I'm going to set it up like this. So you can see there's a reference point, there's a midpoint. So we're going to recreate this part of it. We are going to do a chamfer on this. So we're going to start something like this, and we're going to add another rectangular piece like this for the hook. And we're going to show you how to recreate the sort of curved feature here. It's going to be simply an arc and then cut off what we don't need. So the overall thickness of that, you're going to be really surprised at the thickness of this. Any guesses in the chat how thick that feature is based on the other dimensions we've used? What did I say about the minimum thickness? 5's a good guess. So this feature is the minimum of that 3 millimeters thick. The overall height from the base is that other, actually this one is a little bit higher to give a little bit of clearance. Yeah, it was designed originally to be, it's designed originally to be 5, but the effective dimension here is actually 6. So then it has an arc that goes from this starting point to really right about here, something like that. And we trim off the parts we don't need. There we go. Now we're going to do a mid-plane extrusion. We're also going to cut out this little center section that we don't need because this is a single entity. You can see that we're referencing that center point, and we're going to do a mid-plane extrusion because we haven't really done one of those yet. So I'm going to change from sketch plane. We're going to do, instead of blind, we're going to do a mid-plane extrusion, and the total width is going to be 9 millimeters. Why 9 millimeters? Well, that's what I guess they decided that slot needed to be. So we have now recreated the part minus the fillets and things from the outside. Now, for modifying this part to be able to be 3D printable, there's a couple places where I can tell you from experience the walls are not quite thick enough. One of those is right here at the base. In order to make a part that is injection molded similarly strong, you need to take a wall thickness from about 3 millimeters up to about 6 millimeters in total to be able to make this work well with the with the geometry. Now, where that's not going to work so well is right here. This particular spot is trying to go into a band, and so this really can't be any thinner than that. But we can do some things with the 3D printing to make it a little bit stronger so that we don't have like a stress concentration spot right here in the underside, so that we have a tendency for this section to just want to snap off. So we can do a little bit of modification here. So practically, we're going to do a fillet, and we're going to select that edge. But we're not going to do a 10 millimeter. We're going to do something a little less aggressive. We're going to try about a 1.5 millimeter. So half the thickness of the part, because trust me, I'm a doctor. It's just a thing. Similarly, you could do a chamfer there. The 3D printer can actually kind of approximate a radius depending on what print height you're using there. The overall thickness of the part, what I could do in order to make this just generally quite a bit stronger is I can cheat. And this boss extrude, we're going to do another boss extrude based on the first sketch. So I'm going to go back to features. I'm going to go back to I'm going to step out of the sketch, because in order to do a feature, you have to be out of the sketch. No, I don't want to modify the sketch. See, this is SolidWorks misbehaving. Because of where my part tree is relative to the plane, I need to get away from the plane so that it stops trying to select the plane and I can actually select the drop down. That's another one of those pro tips, things that can cost you time. So I'm not going to do a mid plane. I'm going to do a blind. I'm going to do another 3 millimeters additional thickness, but I'm going to hit this reversey arrow to reverse the direction. So now I have a 3 millimeter additional thickness. So I haven't compromised the portion of the part where it interacts with the buckle. This is the buckling portion that goes into that band geometry. So the band has both a couple cutouts in the center to be able to thread back through this, and it has a couple additional things there. The only other area that I need to do some real reinforcement now, there is a feature here that grabs onto the band to keep it from slipping. So I'll show you how to recreate that real quick. We're going to do another quick and dirty sketch referencing this plane. And what it's going to be is simply a straight line referencing here to here, another line referencing this vertical, and we're creating a triangle here to be able to work as a tooth to bite into the geometry of the buckle itself, or the band. And I'm going to do an extrude, and I'm going to do another quick cheat feature. You guys go to TikToks for hacks. Turns out all you ever had to do was come to me. Up to next. In this case is going to be the quickest. Single click and I'm done. I've now created the tooth that's going to hold on to the ribs in the belt that gets fed through here. So it's going to be a little more work to feed it through, but I'm still going to be able to catch the feature that's going to be almost impossible for you guys to see on camera, but it's there. It's a rib that creates kind of a sharp edge to hold on to and keep the ribs in the belt from slipping and sliding. So it's trying to hold on to that geometry and keep it from moving around, so that when you go to tension it, one part of the band is holding in this direction tightly, another band is holding in the other direction tightly, and the two together work to hold this part in tension. So it's trying to tear the part apart right here in this direction. So this face has a tension, or has a force that's pulling this direction, and this face right here, and subsequently this arch, has another tension force pulling it in the opposite direction. That's why it's in tension. So that's the part that needs to be strong, and that's why I needed to make this additional thickness here. So I don't really need to worry about anything else in terms of the height here. The only other weak dimension is the band at 3 millimeters thick in a 3D printed part. This isn't going to have much torsional resistance to tearing for the band trying to rip the base apart here. So the only actual change that I need to make here is another cheat, and I'm going to create this sketch on this surface. And instead of even creating a sketch, I'm simply going to use offset entities and use that plane. And I'm going to say 0 millimeters. So I've got this sketch. It's not on the plane I had intended, but that's fine. We'll fix it in post. So we do an extrude. Instead of from sketch plane, we're going to do from surface. We're going to do from this surface. We're going to go the opposite direction, blind extrusion. And I'm going to add 3 millimeters to this, because that's going to make this part of this part very, very strong. So that now it has the resistance that it's going to need in order to be in tension and have things looped back and forth through it and be very, very, very strong. So this now has all of the key criteria. The only real weak point here is this beam, but because it's 4 millimeters thick instead of 3 millimeters thick, that's going to be okay because of our 6 millimeter thickness in this dimension. That's actually going to resist any kind of bending force in either direction. We want the thickness in the direction of tension and in the direction of any bending moment, stuff that you guys will learn about later. So we are now actually done with the part and revising it for our specific purposes for 3D printing and making it additive manufacturer friendly. Okay, so any questions on this? Let's get a clarity scale check from 1 to 10. Again, 1 being dry dirt, 10 being holy water. Where are you guys at on that clarity scale? Okay, we should be somewhere around 7s and 8s, and that's what I'm seeing. Good. A handful of 5s and 6s, I expect. Mostly 7s and 8s. So I'm actually going to save this part, which I don't do a lot of during class. I remind you guys to save early, save often for a bunch of reasons. And often if I'm making an actual part, I will do an additive or something like that, and then a revision number. R1 is Rev 1. Probably I should technically do R0, Rev 0, but that's okay. So I am actually going to recreate that in, let's see, I am actually going to recreate that. If you guys are going to start 3D printing some of the parts that you're designing, which I highly recommend, what you will need to do is a save as, and instead of a SolidWorks part, you're also going to need to save as an STL file. Depending on the slicer you're using, you might be able to get away with a 3MF, 3D manufacturing file. STL generally works better with most things. So down here toward the bottom, STL, I'm going to go ahead and include that. So it'll say yes, all the bodies. Then you will load that up into, since this is a process that some of you haven't necessarily seen yet, I will go ahead and show that part of it. Let's see, where is the window? There we go. All right. So this is going to go onto a Neptune. This will be sort of humorous to see the actual scale. So I'm going to go find the part in that folder that I just saved. I'm going to drop that into place, and we're going to see the buckle. I'm going to close this for a minute. I need to do some changes in orientation. I could print it this way, and it would work with the printer. It's not going to be quite as efficient as it could be. The wise way to actually print this for strength is going to be because of the specific stresses and strains that are going on, because there's going to be bending moments back and forth on this specific part. You don't want layer lines that are parallel to the bending moment. You actually want the layer lines to land perpendicular to the bending moment. So it really needs to be in this orientation because you're printing in a raster in X and Y. I'm not using crazy spline things and all sorts of things. It doesn't really matter whether it's this orientation or whether it's 90 degrees out. I'm going to print one in probably this orientation just for the sake of simplicity. It is best to have just a little bit of support under this overhang. Technically, I have the cooling to get away with being able to have this short of an overhang, but it's not advisable to do without any kind of support. So we're going to select the part, and I'm going to include in the settings. I'm going to drop my layer height to 0.2 on this one because I do want fairly fine detail. Walls, this one I'm going to want to do very strong, so I'm going to do a 10 wall count, which is overkill and technically more. There are some fundamentals of really, really good high level design where your wall count should be a multiple of your layer line thickness actually, but it's really more of a linear multiple of your diameter, your actual extrusion diameter. And if you're using a high precision nozzle like I am, I know it's actually exactly 0.6 instead of 0.6-ish. Like a cheap brass Chinese nozzle. The infill density here, I want to use 55% and gyroid. This is essentially going to print as a solid part, but there might be a couple sections where it has a gyroid region. I want this to be pretty much a solid single part. Travel speeds and things I've already got configured. Retraction I've already got configured. Part cooling, since this is PETG and I really want maximum layer fusion, I really don't want cooling. Minimum temp that I want to run is about 245 for layers. I do want to generate support. Tree style is fine. Most importantly of all, this thing, number of walls surrounding the support infill. Support walls are hideodorous. So I'm going to go back to normal support and no wall lines. Trees need wall lines. Normal support doesn't because reasons. And we'll see what this looks like in the preview. So I'm going to reorient the view here. All the 3D softwares and things, some of them use some commonality. So this is the only place we're actually going to see support is in this layer. So we're going to see what it looks like printing layer by layer. And 10 walls is probably technically overkill for this. But I want it to essentially be a solid part as if it were injection molded. If we were to back that off to only 5 and we reslice it, we'll see what the geometry looks like. So 5 is enough that this is part of the parameters that you play around with a little bit. 5 is enough that there's a little bit of infill there toward the center. And this technically would be sufficient to meet my specific criteria because of the 55% infill. This is almost like a solid part. It drops some of the requirements and has multiple layers. So the reinforcing layer, these walls are all solid, which is what I want. If I were to drop that down any further, it wouldn't be sufficient. And the part here, there's sort of, yeah, like 2 or 3 layers of infill technically with that part. This region here is not critical. So I could actually print this. And that's what I'm effectively going to do for this particular application. That gives you a sense of at a 0.6 millimeter wall thickness or 0.6 millimeter extrusion width. If we were to drop that down to 4, how that changes, 4 starts to drop this wall and it's no longer solid. It now has some kind of infill. Now it's effectively going to print almost as a solid. So you could shave just another maybe half a gram of material out of it by doing that. But the other thing that you want to pay attention to is the steepness of that ramp. It's going to have more precision if I were to cut it down to 0.1 millimeter layer heights. That ramp is going to be made of more layers, and so it's going to be a smoother transition, but all I need it to do really is be a lip. So each layer up could be one more step there, and 0.2 is going to give me sufficient definition for what I'm looking for. It'll also change the effective time required. So this is about a half-hour print, give or take. I can probably bump the speed up to get it to closer to about 20 minutes. So that gives you an idea how to take a part that you need to recreate, take measurements, very fine measurements with a caliper, and recreate it using some of these techniques. And this is how we would go to 3D print this. So this is actually a part that I happen to need, and I happen to need it today. So that's what I'm going to go set up. All right. Now that you guys have seen that, questions? Any questions as we go to close out?